Today I'm pleased to introduce Mario Livio, I think I got that right, a well-known and respected astrophysicist and author. He's been in this twice before. Some of you may recall his talk in October of 2004. That was called Beauty in a Dark Universe. And he also visited us in January of 2009, where he discussed his book, Is God a Mathematician? I always thought he was a physicist, but or a chemist. Anyhow, he also has a very vibrant connection through NIST that's sort of being constantly reinvented. He worked for 20 years with Bob Hanisch, and I think many of you have heard Bob's name. He's new on the campus. He arrived here, I think, this past summer. He's currently the director of the Office of Data and Informatics, trying to explore ways to move NIST into the big data world, or the big data universe, I guess. So that, and their relationships have gone on for 2 decades, and I suspect there'll be many more decades, or at least a couple more decades in the future. So in addition to being a prolific author, our speaker today has been in works of popular science and mathematics. He's also a senior astrophysicist at the Space Telescope Science Institute, which operates the Hubble Space Telescope. Consequently, the connection to Bob Hanisch, and this is where they initially got their connection going. He joined the Institute in 1991 as the head of the archive branch, and he also serves as the head of the Institute's science division. He was a professor of physics in the physics department of the Technion Israel Institute of Technology for a decade. That started back in 1981. But in his day job at the Space Telescope Science Institute, Mario is focused on topics including supernova explosions, the nature of dark energy, black hole formation, and the possibility to extract energy from them, and on the emergence of intelligent life in the universe. He's published over 400 scientific papers. But Mario is also a self-proclaimed art fanatic. I mean, most people won't admit to being any kind of a fanatic, but I guess if you have to be a fanatic, art's not a bad thing to be a fanatic about. He brings together his passions for science and art in 5 popular books, in public lectures, and in his blog, A Curious Mind. He has appeared on TV shows, including 60 Minutes and The Daily Show, and has received several prizes for his books. The subject of today's talk, his book, Brilliant Blunders, describes mistakes made by some of the world's preeminent scientists and what we can learn from them. As one of his fans, Nobel laureate Adam Rees from Johns Hopkins said of this book, "It is said that genius is the ability to make all possible mistakes in the least amount of time." Livio's genius is to show us just how much of those mistakes have taught us. Please help me welcome Mario Livio.
Thank you very much. It is and I mean it, it's a real pleasure to be back here and give a colloquium, and I still remember Bill Ott, who invited me the previous 2 times and so on. So, Brilliant Blunders. Let me first say what this book is about and so on a little bit, and then I'll start the actual talk. While I was writing this book, people kept asking me, what is your book about? And I used to say, it's about blunders and it's not an autobiography. Now, why did I decide to write a book about blunders? So the main reason I'll come to towards the end of the talk, but now let me just say that it's kind of comforting to the rest of us to know that even the greatest luminaries make some serious blunders. The main reason has more to do with the way progress in science is often presented, both in school, in the media, and so on, where it's presented as it's some sort of a direct march to the truth. And as working scientists, you know that that is not the case, really. And I wanted to convey that in a more articulate way. Now, I've chosen 5 scientists to discuss in this book. Today, I will only talk about 3 of them, because you can only talk so much in our talk. But let me tell you how those people were chosen and why and so on. So, first of all, I wanted to take 5 true luminaries, and they all are. I will tell you who they are. So they are Charles Darwin, Lord Kelvin, Linus Pauling, Fred Hoyle, and Albert Einstein. Here, as I said, I will talk only about 3 of them. How did I choose those particular people? So one criterion was they have to be true luminaries. Second, I didn't want to go too far back in history, because the thing is that you go too far back. For example, suppose I go to Aristotle. Aristotle was a genius. There is no question about that. But basically, everything he said in physics was wrong. So, that doesn't make him any less of a genius. It's just that, he worked on a different background. So I didn't want to go to a place where, everything he said is wrong, so what do I choose to talk about, and so on. I also chose, for each one of these people that I do discuss, I chose only one blunder, which I discussed. I didn't do a laundry list of every possible mistake they may have made. So that was one thing. So I only went back to the middle of the 19th century, only that far back. The other thing is I did want to have a thread that connects these 5 people. And the thread that connects them in this particular case is the concept of evolution. And by that I mean evolution of life on Earth, evolution of the Earth itself, evolution of stars, and evolution of the universe as a whole. So the thread of evolution goes through the 5 characters that I discuss. So let me now start. And the first thing you notice about life on Earth is how diverse it is. It's enough to go outside here now, and you will see many plants, you will see insects, you will see birds, you will see people, some of them may be walking their dogs, and so on. Nobody actually even knows exactly how many species there are on Earth. Estimates range all the way from 5 million to 100 million. The latest very serious estimate to try to put on this was said 8.7 million. But the reason there is such a wide range is because you take a teaspoon of dirt from under your feet, and there are thousands of species in that already. So lots of species of life on Earth. That's one characteristic. The second thing that characterizes life on Earth is the enormous adaptation and this relationship, this scratch my back and I'll scratch yours type relationship, which we call symbiosis. You look at a bee, and the bee has precisely the size that it fits into the flower on which it feeds. And then, of course, the pollen gets on the bee's body and legs, and the bee transfers that to another flower, and so on. If you look at something like this clownfish that I describe here, this clownfish lives among the poisonous tentacles of the sea anemone. The fish protects the anemone protects the fish. The fish has on its body this special mucus that protects it from the poisonous tentacles of its host, and so on. So very, very high degree of adaptation and symbiosis. Now, these 2 elements, the very large diversity and the high degree of adaptation, have convinced many naturalists over centuries that there must be some guiding hand, design, and things like that. All of that has changed in one shot in 1859, when this gentleman, here shown at old age, Charles Darwin, published his book on the origin of species by means of natural selection. Just as an aside, let me note that when I work on a book like this, and it takes me a long time to write books, 3 to 4 years typically, and the part I really enjoy the most is the research, and I like to go to the places where the people that I write about worked and so on. So in this particular case, I did go and see all of his Darwin's thing. I held in my hand the first book of first edition of On the Origin of Species, and so on. It's a great feeling. I mean, it's something that I mean, there is a lot to be said for the internet, but still holding the book, or first book, is a different feeling than seeing it on a screen. So anyhow, this was his book. And with this one blow, he really changed everything we know. This graphic here about evolution, I've put it here not because it's accurate, which it isn't, but only because I liked it from a graphics design perspective. It's very nice from a graphics design. It's really wrong, you know, because it gives you the impression as if things here are more evolved than things here, and that's actually not the case. You see, evolution is it's not a ladder. Evolution is more like a bush, where things evolve in different directions. But things that are equidistant from the source are equally evolved. It's not that one is more evolved than the other and so on, but it's still a nice graphics design. There is one thing that Darwin never liked to publish, and that was genealogy trees. He never published one. However, he did use them in his notebooks to help his thinking. So here is one that I also held in my hand. So he never published this, but he did draw it to himself. I like this one because it has primates here and man up there. So it's a nice one. But like I said, he never published it. Now, what was this theory of evolution that Darwin came up with? The theory was based on 4 pillars, and those 4 pillars were supported by one grand mechanism. Now, this figure here has nothing to do with Darwin's theory of evolution. It comes from a Hindu myth. But you see, it has 4 pillars, and they are resting on one grand mechanism. So that's why I used it here. Now, there is a story that is almost certainly apocryphal. But it's such a good story that I will tell you nevertheless. But it's almost certainly never happened. So don't ever cite me as if saying as if it happened. And that is that Bertrand Russell, the famous mathematician and philosopher, once gave a talk about the universe and such, and he used this kind of graphic. And then some lady in the audience asked him, on what does that giant turtle stand on? And he said, on another giant turtle. She said, and on what does that stand on? He said, yet another giant turtle. And she insisted, and on what does that? And he said, lady, I'm afraid from there is turtles all the way down. So again, it almost certainly never happened. But you know, there is an Italian proverb, si non è vero è ben trovato. I mean, even if it's not true, it's still a good story. So, okay, so what are these 4 pillars? So first there is the pillar of evolution itself. Namely, Darwin tells us the species are not immutable. The species that we see today on Earth did not always exist. In fact, most of the species that ever existed on Earth got extinct. Today only we see the species that evolved from previous species that existed on Earth. That's the first pillar. The second is that of gradualism. Gradualism is a concept that Darwin borrowed from his geologist friends. In particular, Charles Lyell, who was the greatest geologist of the time, was Darwin's personal friend. So the idea was that just as the surface of the Earth is being continuously changed, but very, very slowly, you know, by erosion and this and that and so on, that's how species evolve as well. Namely, you're not going to sit there and watch a species turn into another species. It happens over tens and hundreds of thousands of generations. So that's that concept. The third concept is that of common descent. Namely, Darwin says, all this diversity that you see of the life on Earth started from one life form. So that's this concept. And this concept is very powerful because, you know, there are people. I have a personal friend, you may know the name, Jack Szostak. He received 1 Nobel Prize already. He works at Harvard on origin of life. He's on his way, in my opinion, to get his second Nobel Prize. But you see, the fact that you can work on origin of life, namely how did life start, is really only possible because you think that life has one kind of, it started from one life form and so on. So that's common descent. And finally, there is speciation, which says, wait a second, I mean, you know, Darwin was aware of this. If all started from one life form, how come that we have such a diversity today? And to that, Darwin's answer is, well, there is branching or splitting. Namely, you have a species, it splits into two, then that one splits into two, and so on. He drew even this diagram in his notes that, you know, shows how this splitting occurs. And since at every such node, you actually double the number of species, very quickly you get to huge numbers. So again, I like this page enormously because look, at the top here, he writes, I think. You see, so Darwin was humble at that stage of his life. So these are these four pillars, and like I said, they are supported by one grand mechanism, and that mechanism is natural selection. There is a philosopher who works at Tufts University, Daniel Dennett. You may have read some of his books. He wrote once that he thought that natural selection may be the best idea, single idea that anybody has ever had in any discipline. Now, that may be a bit of an exaggeration, but it certainly was an incredible idea. And like all incredible ideas, once it's pointed out to you, you say, why didn't I think of that? It looks kind of simple. And the idea is the following. The idea is, suppose you have a certain species. And suppose a few members of that species have a characteristic that gives them some advantage in terms of coping with the environment, with other members, with I don't know what, and also in terms of producing offspring. You know, they produce more offspring. And suppose that that characteristic is inheritable. Then, Darwin says, over many, many generations, the entire population is going to shift towards that characteristic. Because, you know, if those are the ones that survive best and they have more offspring, and that's inheritable, over many generations, that's what's going to happen. This is the idea of natural selection. Now, I just want to give you a couple of examples. So, in England of the 19th century, there was this light-colored peppered moth. And look, originally, it was so well camouflaged that you can hardly even see that it's here. You see that here? Now, what happened is, of course, in 1848, there was the Industrial Revolution. They started pouring enormous amounts of soot into the atmosphere, which blackened all the trees and everything. I actually was shown today this house that looks like my next door neighbor's house, which tries to use greener practices for energy and so on. Basically, what happened is this light-colored peppered moth, you see, it's now sticking out like a sore thumb. So it became the target for massive predation and was on the verge of becoming totally extinct. At the same time, the dark or melanic version of that moth actually started thriving because of it was now better camouflaged. Now, luckily, actually, for this light-colored moth, even in 19th century England, they actually did adopt somewhat greener practices, and the light-colored moth was actually saved from total extinction. This just shows a few examples of rat snakes that, by natural selection, have adapted to the colors of their environment, you know, which of course made them survive better. Now, why does that splitting, you know, even occur? Darwin didn't know the reason for that. Today we know how that actually works. I mean, and it works not just at very low types of life, but even at bigger ones, you know. I mean, like, you may have a whole population of buffaloes that live on the dry side of a mountain range, A few of them wander to the wet side. And then, you know, over many, many centuries, many, many generations and so on, eventually they cannot interbreed. That means you got a new species, you know, and so on. Now, where do we actually see natural selection the most today? We see it the easiest with bacteria. And the reason is that, number one, the populations of bacteria are humongous, and second, they multiply very fast. So the entire process of evolution is compressed. So, as you know, there are now these superbugs, these bacteria that are now resistant to all types of antibiotics. Every year, in fact, now in the US, there are about 22,000 people who die because they are infected by these bacteria that are resistant to all types of antibiotics. Why does that happen? We play a small bad part in this. When I mean we, I say all of us, in the sense that, you know, you have some sort of an infection, doctor prescribes antibiotics for 10 days, you take it 3 days, you feel well, and you stop taking them. Well, that's a good prescription to develop more resistant bacteria. But of course, the main problem has to do with the massive amounts of antibiotics that they feed both cattle and poultry because of the way they raise them. And only just this past year, they finally started to have some guidelines about how much antibiotics you can actually stuff into all these things. So anyhow, there is a problem. But, and we will need to solve it eventually. Now, from everything I told you so far, you can see that Darwin actually had an incredible theory of all life forms on Earth, and it works extremely well. So where is his blunder? I'm talking about blunders. So the blunder had to do with heredity. You see, Darwin didn't know any genetics, and we cannot blame him for that, because nobody knew genetics at the time. So Darwin adopted the theory of heredity that was the prevalent theory at the time. And again, that's not a blunder. He could not have done better. That was the prevalent theory. And the prevalent theory was that of blending heredity, which basically said that the characteristics of the mother and the father get mixed in the offspring in the same way as you would mix paints. That was the theory. Like I said, that in itself I don't regard as a blunder. Darwin adopted what was known. The blunder was in the following, that Darwin didn't understand, at least at first, that by adopting the blending heredity theory, that actually natural selection could never have worked at all if that were truly the correct theory of heredity. Let me try to explain that. Suppose I have a population of 1 million butterflies, or that moth or whatever. They are all white. And there is one black butterfly. And let's suppose that for whatever reason, being black gives you an advantage in terms of offspring and so on. According to Darwin's theory of evolution by means of natural selection, that would have meant that the entire population of butterflies should have turned black over many generations. Now let's see what would happen with blending heredity. The black butterfly would mate with a white butterfly. They would produce a gray butterfly because you mix them like paints. That's it. Black is gone. It will never come back into that population. Not will it not the population turn black. In fact, black has disappeared from the population after 1 generation. That gray butterfly would mate with another white butterfly, produce a paler shade of gray butterfly. Very soon you will have more than 50 shades of gray, you know. But you will not have black again. So really natural selection could not work with this. I mean, everybody knows this, you know. You drink gin and tonic, right? If somebody will keep pouring tonic, you know, at the end you will not feel the gin, right? If you mix them like this. So this would not work. And this, Darwin at first didn't catch this. It was pointed out to him by an engineer named Fleming Jenkins, who wrote a review of his book. Now, it's true that Darwin didn't catch this as a blunder. However, what is also true, that Darwin had a strong feeling that this blending heredity is not the correct theory. And even as early as, let me come back to this, even as early as 1857, Darwin once wrote that he believes that at some point propagation by true fertilization will turn out to be some sort of a mixing and not fusion, not like paints. In other words, what do we know the theory of heredity actually to be? The theory of heredity that we now know is correct one is what Mendel taught us. Gregor Mendel did these experiments with green peas, yellow peas, found a ratio of 3:1 and so on. Basically, what does that theory tell us? It tells us that heredity works not like paints, but more like shuffling of cards. See, if you have an ace, and having an ace is good, it doesn't matter how much you shuffle, you still have the ace. That is the essence of genetics, right? So let's see for a second what happens under blending heredity and what happens under Mendelian heredity. Suppose you have, a quality that I denoted by capital A, and it gives the color black, lowercase a gives the color white. Under blending heredity, you get from one parent this, from the other parent this. You get a gray thing, but it's not just that you get a gray thing. The capital A and lowercase a cease to exist. They fuse together into some new quantity, which is gray. And then one parent gives you this gray, the other parent that gray. That's it. It's gray. You'll never get black again. What happens under Mendelian genetics? This one gives you black, this one white. Together, they still give you gray, but the capital A and the lowercase a continue to exist. And therefore, when now these parents mate, one gives capital A, lowercase a, capital A, lowercase a, and then depending on how you mix them, you may get black or gray or white. And if black gives you an advantage, over many, many generations, the population will turn black. Okay. So Darwin felt that there was a problem, but didn't quite know how to correct it. Then in 1866, he wrote a letter to Wallace, who was the person who suggested natural selection independently of Darwin. And he wrote to him something that, you think about this today, and you say, how didn't anybody think of that? See, what Darwin told Wallace, wait a second, how can this blending work? After all, every female of the world gives birth to a distinct male and a distinct female, and not some intermediate hermaphrodite. So it cannot be blending. Now, here is Darwin on the horse. Now, when Darwin wrote this 1866, there have been no fewer than 4 books that claimed that Darwin's, and he continued to talk later in life about that he didn't believe in blending heredity, even though he didn't know how to correct it. Darwin was, if he had a weakness, he was extremely weak in mathematics. So he really didn't know how to construct a theory with probabilities and so on and this. But he felt that this blending cannot be right. Now, no fewer than 4 books claim that when Darwin wrote this here and later in life, it was not because he thought about this by himself, but it was because he actually read Mendel's paper. Mendel's paper was published in 1865. So this is the kind of thing where I tend to get obsessed about. It's of no real importance, but I decided that I absolutely have to establish whether or not it's possible that Darwin read Mendel's paper, and because of that he got these new insights. Now, luckily for me, Andrew Slater from the Darwin Project did a lot of work before me, so I could rely on his work as well. So, what is the truth? First of all, Mendel's paper was not in Darwin's possession. We know everything that was in Darwin's possession. Mendel's paper was not among those things. That's not surprising. Mendel's paper was published in the Journal of the Academy of Brünn, and Darwin did not subscribe to this. It was a relatively obscure journal. He didn't see that. However, some of those books claim that Darwin had books later, when he talked later about these things, that described Mendel's experiment. It turns out that Darwin had two books that indeed describe Mendel's experiment. Now, one of them describes Mendel's experiment so briefly that there is no way to even tell what Mendel's results were and so on. There's nothing that Darwin could have learned from that. The second book, I asked for it to be brought to me. It is this book. You see, this is Darwin's copy. He even wrote his name here so that nobody will take this book away. This book was written by Wilhelm Olbers Focke. And it's true that it described Mendel's experiment in it. Now, I asked for the book to be brought to me, and this is the book. This is the actual book. Do you know where Mendel's experiment is described in this book? It's here on this page, in these uncut pages at the top. Some of you may remember that there was a time when you had to cut the top of pages. No pages were cut in this book. Darwin never read this book. Now, not only that, let me tell you, I now read what's description there. Had Darwin read that, it would not have been much illuminated, because Focke didn't understand anything from Mendel's experiment, so neither could Darwin. So Darwin did not know about Mendel. I should add that Mendel did know about Darwin. Mendel had a translation to German of Darwin's book. He annotated it. He wrote some things in the margins. He often quoted some things that were almost verbatim from the book, you know, and so on. He never mentioned in his writings Darwin by name, but we can understand that. I mean, Mendel became a bishop, and it wasn't very popular for a bishop to quote Darwin's theories. So anyhow, that was the situation with Darwin. Second person is Linus Pauling. So Linus Pauling is the only person in the history of science to have gotten 2 Nobel Prizes without sharing them with anybody. He got 2 Nobel Prizes by himself. There are a few other people who got 2 Nobel Prizes, Madame Curie, others, but he is the only one who got. Now, one was for peace, but one was for chemistry. Here he is at a relatively early stage in his life, pointing to his model for proteins, which was called the alpha helix. With the years, Linus Pauling became older, but the model stayed the same because it was the correct model. Now, how did Pauling come up with that model? So Pauling wanted to find a model for proteins, and this was in 1948. He was in Oxford. He was on sabbatical. He was sick in bed. He asked his wife to bring in some paper and a ruler, and he started to try to determine the structure of these proteins. Now, I have to tell you a little bit about how Pauling used to work. You see, at that point, people were using X-ray diffraction to determine the structure of molecules, because that process was already known after the work of the Braggs and so on. Basically, if somebody never worked in X-ray diffraction experiments, you take the molecule, you shine X-rays on it. From the way the X-rays are scattered, you try to determine the structure of the molecule. Now, Pauling actually worked the other way around, and he really initiated that type of work. Namely, what he did, he started to try to determine the structure of a molecule using structural chemistry, which meant how are the atoms arranged, what are the lengths of the bonds, what are the angles among the bonds, and so on. How can he construct a model from that? And only after he had a model, he tested the model using X-ray diffraction. So he really came to the problem from the other end. Now, in this particular case, he managed to convince himself that the carbon, nitrogen, and the 4 atoms to which they connect all had to be coplanar. They had to be in one plane, but the rest of it had to somehow arrange itself. So after he did all kinds of experiments, he came up with this model, which he called the alpha helix, which is a fairly complex structure, but he thought that he was very happy with this model. Now, there was one slight problem with this model, which was that in his model, after he calculated all these lengths of bonds and whatnot, the distance between 2 turns was 5.4 angstroms. Now, the X-ray diffraction images showed some signature at 5.1 angstroms. Now, you may think 5.4, 5.1, close enough for government work. This is the wrong place to say that, right? But Pauling worked probably like somebody at NIST would work. He was unhappy with this discrepancy. So unhappy that he waited 13 years before he published his model. And during those 13 years, he did all kinds of things. He asked his assistant, Robert Corey, to do X-ray diffraction of the building blocks of this model. He asked Branson, a mathematician, to see if there is any other possible solution to this structure, which there was, it turned out. There was a solution which Pauling himself also found, which was called the gamma helix. But that did not work because you couldn't fit all the atoms inside there. So they couldn't find any other solution. At the end, after 13 years, he said, okay, as far as I know, this is the correct model. He published it. It turned out to be the correct model. This turned out to be an artifact of the fact that in the molecule there is a coil within a coil, which gave this artifact at 5.1 angstrom. So there he was with this incredible model for proteins. Then Pauling turned his attention to DNA. Now, long before he started working on this, which was in the 1950s, in 1948, Pauling made this extraordinarily insightful comment, which I wish he would have remembered a few years later, but for reasons which you will see in a minute, he didn't. So what was this comment? You see, he said, well, whatever the molecule that is responsible for replication is, which is what DNA is, it will work best if it is composed of 2 parts which precisely complement each other. Because if it is like that, then it is enough for you to have half the molecule, and you already know what the other half is, if it's exactly complementary. So this was an incredibly insightful comment that he made in 1948. He also knew about the Chargaff rules. These were named after chemist Erwin Chargaff, who discovered the following. You see, DNA is composed of 3 components. It is composed of sugars, phosphates, and 4 bases, which for short are called A, T, C, and G. 2 of them are single-ringed and 2 of them are double-ringed. Okay? What Chargaff discovered was that in any piece of DNA that he would take, the number of A's was equal to the number of T's, and the number of C's was equal to the number of G's. Now, this type of a relation also kind of argues for something that's composed of 2 parts, right? I mean, this equals this equals, right? So, Pauling knew all that. Yet, when he finally came up with his model for DNA, it was a disaster. The model had 3 strands. 3. How do you do complementarity with 3? How do you do this with 3? It had the phosphates in the middle, the bases pointing out, which, as you will see in a second, just cannot be. So let's see what his model looked like.
This is Linus Pauling's failed attempt to predict the structure of DNA. The problem with his triple helix model is that the phosphates form the helical core, with the bases pointing outwards. This would be impossible under normal cellular conditions. Each phosphate group is negatively charged, and so many negative charges forced together would repel each other, literally driving the structure apart.
So basically, Pauling's model had the wrong number of strands, it was built inside out, and it didn't hold together. So Pauling suggested that hydrogen bonds can hold it together. But guess what? You know, DNA is a nucleic acid. What is an acid? It's something when you put it in water, it releases its hydrogen, right? Now, how can it release its hydrogen if it is hydrogen that is holding the structure together? So it basically didn't obey the basic rules of chemistry. And this is from Linus Pauling, the greatest chemist to have ever lived. So one of the things I've done in Brilliant Blunders was to somehow try to get into the heads of the people that I described, to try to understand why did they make the blunders they made. Now, this is not easy. You know, first of all, I'm not a psychologist. But even if I were, these people are dead. So I cannot talk to them directly. Now, in Pauling's case, I actually did talk to most of the important people who worked with him who are still alive. You know, his former postdocs, grad students, and so on. But still, you know, today there are other ways too, right? I mean, you can take a person, stick them into a functional MRI machine, and see what they think when you ask them this or that, right? But like I say, these people are dead. Now, in Pauling's case, there are more questions that I needed to answer, but in particular, there were three. The first one was, why the rush? What do I mean by that? Do you know how long it took Pauling from the time he started to think seriously about DNA till when he published his model? 1 month. This is after he spent 13 years developing his model for the alpha helix, for proteins. The second, he seemed to have forgotten everything he knew. What about the Chargaff rules? How did he, you know, his model did not obey those at all. What happened? Third, what about the basic rules of chemistry? The model just wasn't holding together and wasn't an acid. So let me just give you a flavor of what I think the answers are. I discuss it in more detail in the book, but I'll give you a flavor. And like I said, I cannot be absolutely sure about any of these answers, but those are the conclusions I reach. So first, why the rush? Well, Pauling was human, and he was very competitive. He didn't know about Watson and Crick. He hardly knew about them. But he did know that both the group in London, led by Maurice Wilkins, and the group in Cambridge, led by Lawrence Bragg, had better X-ray diffraction images than he had. And he was afraid they will publish before him. So that was one thing. How did he forget Chargaff rules? That's really a guess. Pauling couldn't stand Erwin Chargaff. Chargaff was a very intense individual. Pauling was a rather laid-back individual. They once spent a boat trip together from the US to Europe. Chargaff used to catch Pauling on the deck and bother him with his rules and so on. I almost think that Pauling took out of his head everything that had to do with Chargaff, which makes him even more human, of course. What about basic rules of chemistry? Now, Pauling did not forget the basic rules of chemistry. He wrote the book on chemistry, for heaven's sake. Literally, I mean. Why didn't he do that. I believe that there he simply fell victim to his own previous success. You see, what did he learn from the alpha helix story? He learned that his original hunch for the model was the correct one. And all the tests that he did later only at the end confirmed his original model. And things that looked like a problem, like the 5.1 versus 5.4 angstrom, turned out to be a detail that had to be worked out later. So I believe that Pauling felt that his model was correct, and he knew that the way it is, the model will not hold together or will not be an acid, but he thought that will turn out to be a detail that will be worked out later. Now, of course, the correct model for DNA was discovered by Watson and Crick. DNA is a double helix. The bases are in the middle. A connects with T and C with G, which immediately explains the Chargaff rules. It also immediately obeys the complementarity thing that Pauling was talking about. If you know half the molecule, you know the other half immediately. So this was fantastic. Now, what did Watson and Crick do once they came up with a correct model? What every two young people would do. I mean, Watson was in his 20s, Francis Crick in his 30s. They went to the pub. So this is the place in the Eagle Pub in Cambridge where Francis Crick stood in the middle of lunch and declared, "We discovered the secret of life." So they have a plaque there that marks the place. If you've never been to the Eagle Pub, you should. It's a great pub. It has other interesting things to it. It's during World War II, RAF pilots used to write their names on the red ceiling there, and that's still there, you know, and so on. It's a wonderful place in Cambridge. Now, I showed you Linus Pauling when he was younger, and then he was older. I showed you Francis and Crick when they were younger. Here they are when they were older. Since then, Francis Crick, unfortunately, has passed. Jim Watson is still very much alive and active. I talked to him several times during the writing of the book. I met with him once and so on. So it's wonderful. I've put here one picture from the 1950s of a meeting on proteins that Pauling organized. And I put it here for three reasons. Reason number one, there is a very high density of Nobel laureates in this image. Here is John Kendrew, Nobel laureate. Here is Maurice Wilkins, Nobel laureate. Max Perutz, Nobel laureate. Here is Jim Watson, Linus Pauling, Francis Crick, Lawrence Bragg. Lots of Nobel laureates in such a small group of people. Second reason, I'm sure you've noticed, there is only one woman, Beatrice Magdo from the Brooklyn Polytechnic. In a meeting on proteins today, I would say it's probably very much 50-50. So some things have changed. And there is a third thing that has changed. You see, I'm looking at you, and you look like I look every day, and like I look when I go to a science meeting. Namely, I don't wear a tie. When I go to science meetings, nobody wears a tie. Meetings of business people, of lawyers, sometimes medical doctors, you know, would wear ties at science meetings. But generally, we don't. Here, everybody, for heaven's sakes, wears a tie. So some things have changed since then. Okay, I'm going to my last person today, which is Albert Einstein. This is my favorite picture of Einstein, because when my hair gets a bit longer, it looks just like that. Now, people once asked me if that's the only similarity I have with Einstein, and I like to say that Newton is dead, Einstein is dead, and I also don't feel so well. Now, Einstein, of course, did lots of stuff, but I'm talking about his theory of general relativity. General relativity, he published the paper in 1915. We are celebrating this year 100 years to his paper on general relativity. This is a paper he wrote to George Ellery Hale in 1913, explaining to him how the sun will bend light rays from a more distant star. Now, what is Einstein's theory of general relativity? Here it is. Some of you may be a bit rusty on your general relativity, so I thought I'd explain it in very briefly. So for a second there, forget about this term. What does this term in the equation, I mean, this is a set of equations because these are tensors. So this is the energy momentum tensor, which means basically that's the mass energy content of the universe. Okay, that's that. This describes the curvature or the geometry of the universe, of space-time. Okay, this is the curvature of space-time. And G is the strength of gravity. So what does this equation tell us? It tells us that it's the mass energy content of the universe that determines the geometry of space-time, and that the force that we call gravity is in fact just a manifestation of the curvature of space-time. Very simply, you see, what Einstein tells us, gravity is not some mysterious force that acts across distance. It is just a manifestation of the curvature of space. In other words, you know, like when I stand on a trampoline, I cause the trampoline to sag. If I will now throw small balls onto this trampoline, they will find the shortest paths in this curved space. That's what the sun, say, does. Sun warps space-time in its vicinity. The planets simply find the shortest paths in that curved space. That's the essence of general relativity. It basically says that mass tells space how to curve, and space tells the mass how to move. That's the essence of GR. Now, in 1917, Einstein tried to apply this new theory of his to the universe as a whole. And he discovered that there is a problem. And the problem was that, you see, he didn't know about galaxies. He only knew about stars. No other galaxies than the Milky Way were known still at the time. But he knew about stars. And he assumed that the stars, not planets and so on, but the stars are actually fixed, that the universe is static, because he thought that was the most elegant solution to his equations. But how can it be static? If everything attracts everything else, then this thing should simply collapse. It cannot stay static. So what Einstein did is he added this term, and this is known as the cosmological constant. And what this term did was that at every point in space, if there was an attractive force in a certain direction, it added a repulsive force exactly equal and in the opposite direction, so that the thing will be in equilibrium. Okay, at every point in space. And he was very happy with this. Now, it turns out this was not a good solution for this problem, because, I mean, even though, yes, I can, this was an unstable equilibrium. If I can balance this thing on my finger, but then, you know, the slightest perturbation will cause this to fall, right? So that was also a situation like this, but Einstein wasn't aware of that at the time. He was happy he created a stable, an equilibrium. Now, then, in the 1920s, these two gentlemen here, this priest and cosmologist, Georges Lemaitre, and Edwin Hubble, after whom our telescope is named, discovered that our universe is not static, it is expanding. Once they discovered the universe is expanding, and Einstein heard about that, he said, well, wait a second. If the universe is expanding, I don't need to have equilibrium at every point, because all that gravity will do is it will slow down the expansion. Yes, like, you know, if I throw something up, right, the gravity of the Earth slows it down. It's not in equilibrium at any point, right? It's only gravity that acts upon it. But if it's expanding, gravity just slows it down. So Einstein took that term out of his equations and regretted having ever put it in there. Now, there is a whole question whether or not he called it the biggest blunder he has ever made. And that's, again, one of those things that I become obsessed about, and I discuss at great length in the book, and you will have to read about this. What do I think about that? But in any case, it did take the term out of his equation. Now, in 1998, two groups of astronomers discovered, by looking at very distant exploding stars, we call type 1a supernovae. Here you see this galaxy here, and suddenly this point of light appears. This is a type 1a supernovae. These are very bright. We can see them more than halfway across the universe. Now, if we see them more than halfway across the universe, it means we get a glimpse of the universe as it was billions of years ago, right? You see something that's 7 billion light years away, it means you see light that left that thing 7 billion years ago. So you can compare, basically, the expansion of the universe then to the expansion of the universe now. What did they discover in 1998? That not only is the expansion of our universe not slowing down, it's speeding up, it's accelerating. The expansion is accelerating. It's, you know, like I will throw something up, not only it's not being slowed down, it accelerates. So it's being pushed on by something that causes it to accelerate. We call that something dark energy. Now, what is that thing that's pushing the expansion of the universe to accelerate? As far as what is this dark energy? Believe it or not, as far as we can tell, it's that term that Einstein took out of his equations. So if Einstein did a blunder at all, it was not putting that term in. It was taking it out. See, some people are just so smart that even when apparently they made a blunder, it turns out to be a big insight. So had he not taken that out, he could have predicted the acceleration of the universe. But he didn't. Okay, I come now to the end of the description of the three scientists I wanted to describe to you, but I now come back to the question of brilliant blunders and so on. So, you see, progress in science is often described like this: a direct path from A to B. I think that nobody knows better than you that progress in science is more like this. It's a zigzag path with lots of false starts, many blind alleys, many times where you need to go back to the point from which you started. Right? But it's more than this. We have developed a culture, which I'm trying now to combat, where you're not allowed to make mistakes. And here is now my main point. You see, there are various reasons why people make mistakes. Let me explain first which mistakes I don't advocate. I advocate against. I advocate against mistakes that are made because you are being sloppy, or because you are not being thoughtful enough, or because you are being inexperienced. You should never be sloppy. You should always be thoughtful. And if you are inexperienced, you should ask for guidance. So those I don't advocate. However, we all like, and I'm sure that here more than anywhere, for people to be able to think outside the box. Well, guess what? When you think outside the box, you may make a mistake. Now, I'm not advocating against incremental progress in science. There is a lot to be said for that. But every now and then, you should allow for some thinking that is outside the mainstream or unconventional. And when that is thoughtful, you should even encourage that, because that occasionally can lead to breakthroughs. And you never know where the breakthrough is going to come from. I mean, you know, suppose somebody told you 20 years ago that, you know, there is one small invention that is going to come, and that's what the world is waiting for. And it is a mechanism that allows you to send a message of 140 characters. What would you have said? Said, are you nuts? Who needs something like this? Well, guess what? By now, entire revolutions have been spawned using this mechanism. So you never know where the breakthrough is going to come from. Now, places like this, and like the entire startup industry, don't need me to advocate that these things that I call brilliant blunders are a necessary part. You see, in startups, right, 4 years down the road, more than half of the startups fail. Now, they fail for various reasons, but partly because they are trying to think outside the box, right? With Hubble, we actually adopted the mechanism by which 10% of the telescope time, by the way, today is the deadline for proposals for the Hubble Space Telescope for this coming cycle. The reason I can be here is that I'm a theorist and I already put in my input to a few proposals on which I am. But there are people who will be working all the way till 8 p.m. today to submit their proposals. Now, we allow for 10% of the telescope time as director's discretionary time for proposals that are either very large and wouldn't be appropriated through the normal time allocation committee process, or think in somewhat unusual terms and things like that and so on. So I'm advocating a process like this that allows for brilliant blunders. Now, I'm almost sure that many of you know about a story that is also apocryphal, but is still a great story, about the barometer problem. The story goes like this, that there was an exam in which the students were asked, how would you measure the height of a very tall building using a barometer? And one student answered something, and he was failed. And then he complained, and then a second professor was asked to look at his answer and to talk to the student. And the student suggested 10 ways to use the barometer to determine the height of that tall building. So one of the ways was that he would drop the barometer from the roof and measure the time it takes it to reach the ground. A second was that he would take the barometer and put it against the wall of the building and use it as a yardstick and measure the thing. A third was that he would hang the barometer on a thread and use it as a pendulum at the top and at the bottom of the building, and determine from the changes in G would determine the height and so on. And one which I like best is one in which he said that he will go to the custodian of the building and tell him, look, I will give you this very nice barometer if you tell me the height of the building. Now, the professor asked him, don't you know what answer we were expecting? And, you know, which was to measure the pressure at the top of the building. He said, of course I know this, but there is no reason why I should give you that answer, he said. The story continues and says that the name of the student was Niels Bohr. Now, it almost certainly never happened, but it exemplifies what I'm talking about. Namely, one way, for example, to encourage this outside-the-box thinking is not to have all your exams as multiple choice. Because if the exam is only multiple choice, it means that if you marked the other answer, it's wrong, right? So you need to give some place where you can actually look at the thought process. I'm not saying, you know, it's good to have multiple choice exams because you can have more of them and you can check them more readily. But every now and then, allow for something that allows you to see the thought process and so on. So basically, my point at the end is that scientific blunders, and by that I mean these things which I call brilliant blunders, can actually be the portals to discovery. Thank you. We're running a little bit late, but maybe if there are a couple of questions,
absolutely. If you have a question, there's
I'll be happy
microphone.
to
Can you go
answer.
to the microphone on the side? That would be really helpful for our friends in Boulder.
Any questions? There must be some questions, right?
Somebody.
Yes. Where do I find what? The book of Charles Darwin? Oh, where do you find the book of Charles Darwin? The book is actually available. I mean, not the... Oh, you mean the actual book? That's in Cambridge. Yeah. Okay, that's in Cambridge. No, because you can find various very nice versions of the book. In fact, there is an annotated version which I find very, very interesting because, you know, it adds all kinds of nice comments on the side, you know, and so on. And this. It is fantastic reading. I mean, Darwin, in addition to being as smart as he was, he could really write. So, you know, you read it today and it reads almost like a novel. It is fantastic. Yes, any other questions?
There's one at the microphone over there.
Yes.
Hi, I'm sure that's...
You're
It
good.
works,
You're
it
good.
works.
Okay. I'm sure that's a composite image, but the planetary body or whatever, was that... What planet is that, do you know?
This thing here?
Is that just Earth?
That's the Earth.
Okay.
But it is a composite image. That's one of our Hubble deep fields. So, yes.
I think we got some more.
Any other questions?
Yep.
Yes.
So it seems like another theme of all these blunders is that these people are trying to operate significantly beyond where the data that they've got. That, you know, Darwin had no idea of
Heredity.
And it seems like the game is to make your blunder, you know, it's almost like an Occam's razor that you're going to have a theory that way over covers the data that you've got, and basically everybody's going to make a mistake there.
Well, it's true that, you know, these people try to really extend, you know, theories beyond this thing. But it's not that they try to operate outside the data of they had, in the sense that whatever they thought they were suggesting was supposed to be consistent with the available data, only that data weren't enough, you know. But this is how science progresses anyhow, right? I mean, you know, people like, I don't know, Karl Popper taught us that you can never prove a theory right, you can only prove it wrong. And the idea is that theories have to be falsifiable. Namely, you create a theory that agrees with all available data, but as soon as new data falsify it, you have to modify or throw away the theory, right? So,
I think we have two more questions. There's one woman over there at the mic, and then Bill, and then we'll break.
Hello. Yes, I was wondering if you could tell us one of your brilliant blunders. Writing your book, you must have thought about something.
So nothing I've ever done is as brilliant as the people here have done. But I do have a story that is not quite a brilliant blunder, but it's sort of interesting for its own right. And that's the following. This was actually when I was very young. I was just out of my PhD. There are these objects we call planetary nebulae, which are what our sun is going to do as well. I mean, the sun later in life, towards the end of its life, is going to eject its outer layers, and then the hot core irradiates all that and causes these fantastic objects that we see. Everybody thought that all the planetary nebulae that we knew had single stars at their center. And then suddenly, some French astronomer came up and said that in 6 cases, it happened to have been a she found that the central stars of these planetary nebulae were not single stars, but they were binary stars. two stars revolving around their center of mass. As soon as I heard that, I actually decided to develop a theoretical model for what happens if you have a binary star. And I did develop a model, quite detailed, which explained how it shapes the nebula and things like that. And I was very happy with it. Soon thereafter, another astronomer looked more carefully at those 6 objects and showed unambiguously that those 6 objects had single stars at their center. So here I was with my beautiful model, but which apparently explained no known phenomenon. So I was quite unhappy about this. As it turned out, later many astronomers started observing these things, and they found that actually most planetary nebulae have binary stars at their centers, to the point that they think that actually maybe even all stars are binaries or were binaries at some point, which merged together to form these things. So my theory turned out to be actually good at the end. So it was a happy ending.
Go ahead, Bill.
Mario, I'm just curious as to whether there were 4 or 5 other blunders that were on your list of 10 that you must have shortened down to 5. Were there any other blunders? For example, in the discovery of fission, there was a lot of published papers that failed to come up with the right explanation.
Look, the history of science is full of blunders. You see, if you take Einstein alone, about 20% of his papers contain mistakes, including the paper in which he derives E equals mc squared. So there are many, many things. But as I said, I chose 5 luminaries, chose this. I will tell you that at one point, I did think hard about, do I want to include Isaac Newton in all of this? But it turned out that Isaac Newton was one of these very annoying people where almost everything he did in physics was right. He almost made no mistakes. Now, he made mistakes in his entire study of alchemistry and things like that. But in his physics, he was just amazing. So, so I did consider a few other people, but at the end decided to concentrate on 5.
Well, thank you very much. Let's all thank Mario.